At least 3 people are dead and a state of emergency has been declared in the Philippines after Super Typhoon Fung-wong made landfall just days after another deadly storm ripped through the country.
On November 9th, 2025, satellite feeds captured something that made meteorologists around the world stop in their tracks. A swirling mass of clouds over the Philippine Sea tightened into a perfect spiral, its eye clearing with terrifying speed. News anchors warned of a Category 5 monster barreling toward land, and yet just days earlier, forecasts had predicted nothing close to this level of devastation. Super Typhoon Uwan should not have grown this fast, not according to any model, not based on any historical pattern we had on record. Scientists had been tracking the system since early November, feeding data into the most sophisticated prediction algorithms ever built. And still, they were blindsided by what unfolded. So how did a storm that seemed predictable suddenly break every forecast and shatter the confidence of an entire field? The answer is not just written in the winds above. It is hidden in the ocean below, in a layer of heat so deep and so powerful that our models never saw it coming. The story of Super Typhoon Uwan begins quietly enough, with a broad area of low pressure that formed northeast of Chuuk on November 3rd. At first, there was nothing unusual about this disturbance. The Philippine Sea in early November is typically warm, with surface temperatures hovering around 29 to 30 degrees Celsius, well above the threshold needed to fuel tropical cyclone development. What caught forecasters' attention was the favorable atmospheric environment surrounding this developing system. Wind shear remained low, allowing the storm to build vertically without being torn apart, and abundant moisture provided the raw material for sustained convection. By November 7th, the system had been upgraded to a typhoon and given the local name Uwan by the Philippine Atmospheric, Geophysical, and Astronomical Services Administration. Meteorologists expected gradual strengthening as it tracked westward toward the Philippines, giving coastal communities several days to prepare. What they didn't anticipate was that beneath the surface, conditions were already in place for something far more catastrophic. Then, in less than 24 hours, everything changed. Between November 8th and the morning of November 9th, Uwan underwent what meteorologists call rapid intensification, where a tropical cyclone's maximum sustained winds increased by at least 56 kilometers per hour within a single day. But Uwan didn't just meet this threshold, it obliterated it. Wind speeds surged from around 120 kilometers per hour to an astonishing 185 kilometers per hour in the span of hours, with gusts reaching 230 kilometers per hour by the time the storm achieved super typhoon status. Satellite imagery showed the eye clearing and contracting with frightening speed, a telltale sign of a storm feeding on an extraordinary source of energy. Forecasters scrambled to update warnings as live data feeds revealed intensity readings that exceeded what their models had deemed possible. The storm's structure became so well defined that even seasoned meteorologists found themselves stunned by the sheer velocity of its transformation. This wasn't gradual strengthening. This was an explosion of power that defied every prediction algorithm designed to anticipate such events. The question on everyone's mind was haunting. What could fuel a storm with this much power? How could it gain so much energy this quickly? The answer lies not at the surface of the ocean, but in the depths below. Most people understand that tropical cyclones draw their power from warm water, but what matters is not just the surface temperature, it is how deep that warmth extends. This is where ocean heat content becomes critical. In most parts of the world's oceans, the warm layer near the surface extends 50 to 70 meters down before colder water begins. When a powerful storm passes over, its fierce winds churn the ocean, pulling colder water upward and effectively cutting off the storm's fuel supply. This natural cooling mechanism acts as a brake on intensification, preventing most cyclones from reaching their theoretical maximum strength. But the Western Pacific Ocean, particularly the Philippine Sea, is different. Here, the warm layer can extend 150 meters or more beneath the surface, creating what scientists call a deep warm pool. When Super Typhoon Uwan tracked across this region, it encountered conditions that allowed it to intensify without restraint. Even as the storm's winds churned the surface waters, the water rising from below remained warm enough to continue feeding the system. The thermal reservoir Uwan tapped into was roughly the size of France, and just as hot 100 meters down as it was at the surface. This invisible layer of heat made the storm almost unstoppable, providing continuous energy that allowed it to rapidly intensify far beyond what forecasters had anticipated. If you are fascinated by how the ocean shapes the planet, consider subscribing. It helps this channel keep exploring the science behind Earth's most powerful forces. Modern weather forecasting is a marvel of technology and science, combining satellite observations with complex physics-based models and increasingly sophisticated artificial intelligence algorithms. These systems have become remarkably accurate at predicting a storm's path, often projecting a typhoon's track days in advance with impressive precision. But predicting intensity, how strong a storm will become, remains one of the greatest challenges in meteorology. The models that forecasters rely on are built on assumptions derived from historical data, patterns observed in thousands of previous storms, and our understanding of how the ocean and atmosphere interact. But those assumptions did not account for what Uwan encountered. The rapid intensification that propelled this typhoon to super typhoon status happened so quickly that traditional forecasting systems simply could not keep pace. AI-driven models, which have shown promise in recent years, also underestimated the storm's explosive growth because they lacked critical information about subsurface ocean conditions. Data from ocean buoys and autonomous Argo floats that measure temperature and salinity were too sparse in this region to capture the true extent of the warm water layer below. Forecasting centers found themselves updating intensity warnings in real time, trying to match the reality unfolding on their screens with predictions that had already been overtaken by events. The chilling takeaway from Uwan's rampage is that we have built incredibly sophisticated models to predict storms, but we still do not fully understand the ocean that powers these monsters. On the evening of November 9th, Super Typhoon Uwan made landfall over Dinalungan in Aurora Province, with winds of 185 kilometers per hour and gusts exceeding 230 kilometers per hour. The storm's diameter had expanded to 1,800 kilometers, meaning its effects were felt across virtually the entire Philippine archipelago. More than 1 million people had been evacuated from vulnerable coastal areas, but the storm's sudden intensification meant that many communities had less warning time than they desperately needed. The country. The region was already reeling from Typhoon Kalmegi, which had struck just days earlier, killing nearly 200 people. At least 2 people lost their lives directly to Super Typhoon Uwan, with widespread flooding submerging parts of the Bicol region and storm surges battering Catanduanes. Power outages affected more than 184,000 customers across Luzon and eastern Visayas, while water levels at Laguna de Bay exceeded critical thresholds. The relatively low death toll is a testament to the Philippines' well-developed evacuation systems and the resilience of communities that face an average of 20 typhoons each year. But it also underscores a troubling reality. Forecasts couldn't give people enough advance warning about the storm's sudden surge in intensity. Scientists now point to Uwan as a critical case study in how climate-driven ocean warming is making super typhoons not just more powerful, but harder to predict. New initiatives are being developed to deploy additional deep ocean sensors throughout the Western Pacific and integrate real-time subsurface temperature data into intensity forecasting models. But Super Typhoon Uwan's story doesn't end with landfall. It opens a troubling window into the future. Ocean temperatures in the Philippine Sea and throughout the Western Pacific are rising year after year, a trend directly linked to climate change. The deep, warm pools that fueled Uwan's rapid intensification are becoming more common and more extensive. The warm water that once characterized only certain seasons and regions is now more widespread and more persistent. It is spreading both geographically and deeper into the ocean column. This means that the boundary between what we consider a strong typhoon and what we classify as a super typhoon is beginning to blur. Storms that in previous decades might have peaked as Category 3 or 4 systems now have access to enough oceanic heat content to push them into Category 5 territory, where the destruction they unleash becomes exponentially more severe. Scientists studying these trends describe storms like Uwan not as anomalies or outliers, but as previews of what is to come. The concern is not just about stronger individual storms, it is about the increasing frequency with which these rapid intensification events occur, making it harder for vulnerable populations to prepare and recover. If the ocean keeps warming at its current pace, how many more storms will shatter the rules we have built our predictions on? Super Typhoon Uwan did not just break records, it broke our understanding of what the ocean can unleash when conditions align in ways we are only beginning to recognize. The storm revealed the dangerous gap between what our models assume and what nature is capable of delivering. For the millions who lived through Uwan's fury, and for the forecasters who watched as their predictions failed to match reality, this storm was a wake-up call that resonates far beyond the shores of the Philippines. It is a reminder that the ocean holds secrets in its depths, invisible reservoirs of energy that can transform a manageable threat into a catastrophe in the span of a single day.